I also want you to know that I'm going to use you as guinea pigs because this is the first time that I'm giving this talk. This talk is called A Tiny Bit of Progress in Understanding the Relay Channel, and it's largely work done by Rhonda Bora, one of the students in my group. So let's put a disclaimer in place. Basically, if there's anything that you like about this talk, you can safely assume that Ron came up with it. And if there's anything that you don't like about this talk, you can safely assume that I botched the delivery based on what he explained to me. So credit is due where credit is due. We had some discussions with Professor Shlomo Shammai and with Gerhard Kramer, and these turned out to be, as you will see later in the talk, these turned out to be very useful suggestions that we got from them. So we should acknowledge their contributions there as well. And well, I'd also like to thank NSF for basically footing our bills so far. Okay, so this is the outline of my talk. I broke it up into 5 main parts. The first part is going to consist of a review of what is known about the relay channel. We'll describe what it is and describe the 2 main coding strategies known for it. Then in the second part, it's not very long, it's about 4 or 5 slides, but this is going to be the denser, the most technical part, so I'll ask you to bear with me for a few slides there. This is what I'm going to explain, what's our contribution. Then we're going to take this coding strategy that we're developing here, and to try to gain. This is basically going to be another coding theorem of the similar type as before. So then to get some insight for what this coding theorem says, we're going to specialize it to 2 different cases and see what we can get out of it. One of them is going to be a case with multiple relays, and another one is going to be the Gaussian relay channel. And then I'll wrap up my talk with some concluding remarks. Okay, so please, like I said, you're my guinea pig, so let's make this as interactive as possible. Please feel free to stop me anytime. Okay, so for the first part, we start with a problem formulation, and then the 2 main known strategies for the relay channel. So relay channel. Any talk on this problem has to start with this slide. It was a channel introduced by Van der Meulen in 1975. It consists of an encoder and a decoder, which the encoder, as a function of a message it picks an input to the channel, and a signal shows up at the decoder, based on which the decoder is going to estimate what was the message sent by the encoder. Now, the addition here, the part that makes it interesting, is the relay. This relay node is going to get an observation from the channel, and it's going to inject some information into the channel as well, with the goal of helping the decoder decode the message W. It may or may not attempt to decode. There's no requirement that the relay has to decode. The relay is only there for the purpose of assisting the communication between the encoder and the decoder. And so we model this channel as having as a conditional distribution with 2 inputs and 2 outputs. X is the symbol inserted by the encoder into the channel. X1 is the symbol inserted by the relay. Y1 is the observation of the relay, and Y is the observation of the decoder. And so we're going to focus on the discrete memoryless setup. So we're going to assume that we have these 2 input alphabets which are finite, 2 output alphabets which are finite, and then this is a conditional distribution that describes the channel. So how do we code for this channel? Well, the first example that one might think of leads to a strategy that we'll refer to as decode forward relaying. So what the relay does is it tries to decode the message transmitted by the encoder, and then as a function. So once the relay figures out exactly what was the message that the encoder was trying to transmit, he will pick an input to the channel that will help the decoder also figure out what that message was. So since we are imposing now the requirement that the relay node has to be able to decode, then we're going to have some constraints on the amount of information that can that can flow through this channel. In particular, how much information can go from the decoder to the relay? Well, we know, so we have a distribution of this form, and we're good for the channel, and we're going to pick an input distribution for x and x1, and based on that we're going to evaluate this mutual information expression. And so for a particular distribution that we fix, the total amount of information that can go from the encoder to the relay is mutual information between x, which is the channel input, and y1, which is the channel output, given x1. The relay know what are the symbols that he's putting into the channel, so he can cancel out that effect. And so basically you have this much rate that can flow from the encoder to the relay. Whatever rate the decoder is going to be able to figure out, since we're imposing the requirement that the relay has to be able to decode, cannot exceed this quantity. Similarly, the relay is going to send a message to the decoder, and that message is going to, if we hope to be able to decode that message cannot exceed the rate of the point-to-point link between the relay and the decoder, and that's the mutual information between x1, which is the channel input of the relay, and y, which is the channel output. So if we combine the information that comes from the relay and the information that comes on the direct path from the encoder, adding up these two terms together, we get another constraint, which is the mutual information between x1 and y, right? And that is going to also put a limit on the transmission rate. And so if we take the minimum of these two quantities, we get an upper bound on the achievable rates, which is the upper bound delivered by this coding strategy. And this is achievable for any arbitrary distribution between x, x1, y1, and y, which agrees with the given channel. So the first observation that we make here is that, and by the way, this is a classical result of Covenant and Ramallah. It was published in a paper in 1979. So what we see here is that since we introduced the constraint that the relay node has to be able to decode, for this to be a useful strategy, for this to be able to achieve higher, for the relay to be useful, for using this kind of construction, for us to be able to transmit more information than what would go directly from the encoder to the decoder, having the relay output a constant signal, we need that the mutual information between, so basically we need that the information on this path be greater than the information on this path. Because if not, if this is the limiting factor, we are better off by just ignoring the relay and sending information directly to the decoder. Okay? So, since there are channels for which in which that is going to happen, so if we have a noisy relay, if we have a weak link between the transmitter and the relay, this prompted the same authors to consider a different coding strategy. And that coding strategy is what's usually known as estimate and forward, or some people also call it compress and forward. In this case, the relay does not decode the source message, but instead it uses compression to turn its channel output y1, which is the vector of outputs that he observes, into an approximate representation of that y1, and then send that to the decoder. Now, why do we say that he uses compression? Well, you can see that both y1, which is the output at the relay, and y, which is the output at the decoder, are conditionally independent given xn, but in general, but they're not. I mean, it's like they both contain information about xn. So if we would like, so if we have yn already available at the decoder, then in order to communicate y1 or some approximation of y1, well, there's some side information available here that we can use in a Wiener sieve type of fashion to compress this information. So that's exactly what this coding strategy is going to do. We are going to represent the output y1 using an approximation y1 hat. We are going to index all of these y1 hats with a message index m, and then we're going to do binning of these indices like we do in the construction of Wiener sieve codes, and we're going to send a bin index s to the decoder, and this bin index s is going to determine the message that the relay inputs into the channel. And so what does the decoder do here? Well, the decoder gets its output. From there, it recovers the bin index s. Then looks at the previous output of the channel, at the previous block that it received, and based on the bin index and that previous output, it decodes, it recovers which one of all the approximations in that bin, which one of all the channel output approximations in that bin corresponds to the one that was observed by the relay. So that's one joint typicality test that is performed there. And finally, once he has the previous approximation and and its own output, he's going to go looking for a source message which is jointly typical with both of them. And with that coding strategy, it is also proved in the paper of Kovra and Gamal in '79 that these rates are achievable. So it's the mutual information between x and y1 given x1, and this kind of intuitively makes sense, because what we're saying is that the rate that we can communicate is whatever information about x is contained between y and y1 hat together. Y1 hat represents the encoding sent from the relay to the decoder, but we have to take out the knowledge about x1, because x1 is something that we're able to decode at the decoder, and so that becomes known information. But we also have a feasibility constraint here, and the requirement is that this quantity here, which represents the information, the common information between y1, which is the channel output, and y1 hat, which is the message that we send, given x1 and y, so that's the information that gets effectively transmitted from the relay to the destination, this has to be less than the capacity of the link from the relay to the destination. So that's where this feasibility constraint comes from. And we also note that for the joint distribution that we use to evaluate these quantities, whereas in the code and forward we had no restriction on x and x1 being independent, they could be correlated in any arbitrary way, here we're going to generate codebooks independently at the transmitter and at the relay, and so we require that x and x1 have to be independent variables. Okay? Two things that I want you to remember from here. One of them is the fact that we have this feasibility constraint, which is going to be the source of many problems, and another one, the fact that we have this auxiliary variable here, which depends on which depends on other parts of the code, but essentially which is going to represent our information that goes from the from the relay to the receiver. I would like to argue that although decode and forward is a well understood strategy, estimate and forward is a much harder beast to deal with. There's a general mapping that is used at the relay, and a priori, the general coding strategy doesn't say anything about what this mapping should be. We don't have any cardinality bounds on this variable. All we know is that for every finite alphabet size, if somehow we could solve the maximization problem of looking for the maximum mutual information subject to this constraint on the distributions, then for each possible cardinality we would get something that is achievable, but we would never know whether if we increase the alphabet a bit more, we're going to get higher rates or not. So it's borderline non-computable in that sense. There's also the fact that even if an oracle came and gave you one of those cardinality bounds, that rate maximization problem is a non-convex problem. Writing down this, the way to see that this is a non-convex problem is, Ron tells me he wrote all the derivatives. He got some nasty subtle conditions. He wasn't able to get a nice closed form optimization problem. But an early hint that you can get that that this is not going to be an easy problem is that basically here I'm going to hand wave a bit, but just to give you some intuition for why this is not an easy optimization problem. We can write this quantity here as mutual information between x and y given x1 plus mutual information between x and y hat given x1 and y. Okay. The first term in this sum does not depend on this quantity, so that's a constant that we can take out of the optimization. The second term, it's the second term is a conditional mutual information that depends on this quantity. Now, if you think, for example, of the classical rate distortion problem, there you have a mutual information expression that you're trying to maximize, and you fix the input distribution and you optimize over the channels. But what you're trying to do there is you're trying to solve a minimization. So if we were trying to minimize as a function of this, perhaps there would be some hope. But what we're trying to do is maximize which one is convex or concave? This way. Convex. So we're trying to maximize a convex function. So basically what we have to do is find some of these boundaries. And
that's very hard.
Well, we didn't know how to. I mean, if you know how to do it, let us know.
I'm just asking.
I don't. We couldn't think of a good way of dealing with that. So maybe there is something to do there. We couldn't find it. So that's another problem with this. Now we go to the multiple relay case, and the number of constraints of this form will increase very fast. We will see that, for example, no, actually we will not see. This was proved in a paper of Gerhard Kramer, I think, that the number of even for two relays, the number of constraints in the feasibility expression, I think it's 9. So it becomes difficult to deal with very fast. And even if I give you a really simple question about estimate and forward, it's going to be hard to answer. Like, for example, I give you a channel. Here's a distribution. And I ask you, for this channel, which one is going to do better, decode and forward or estimate and forward? You don't know how to answer that. I don't know how to answer that. So
You were saying you don't know the answer because you don't know how to...
Because I don't know how to deal with these problems here. Right. 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 So, the conclusion is that whereas the code and forward is much closer to what we would normally call a nice solution to a coding problem, estimate and forward is more of a general framework of coding strategies, but it's not a nice simple coding strategy that you can analyze, and so we want to do something about that. Yes, go ahead.
Does it become any simpler if you consider Gaussian? I mean, there is always an analog between Gaussian and discrete.
We'll talk about the Gaussian problem in the Gaussian setup in the fourth part. Let me defer the answer to there. And it won't be a complete satisfactory answer, but I will show you some difficulties that we had to deal with even in a simple Gaussian example.
So the estimate and forward does, the difference was there's no coherent combining between the relay and the, let's say in the relay and the source, like the second term which was there in the decoder and forward, that was not there in, like in decoder and forward I had an I of x, x1 and y in the second term.
This one.
Yeah, so this was missing in estimate forward, or that one?
It's not that it's missing. It's a different flow of information. So your code works in a different way. Here you're forced, in the code and forward, you're forcing the relay to the code.
Yeah.
Then the relay gets the same information as the transmitter, and then they can, both the transmitter and the relay can, since they agree on what's the information that they're trying to send to the decoder, they can do things like coherent combining, like you were saying. They have this common information. In this case, they don't. So all the relay is doing is it's saying, look, I'm going to give you my output of the channel, or some approximation of it that that the channel will allow me to send you. You figure out what to do with it. That's essentially what EAF does. Okay, so now that I hopefully convinced you that estimate and forward is an ugly beast to deal with, let me tell you a little bit about our choice of an auxiliary variable to try to get some insight there. So consider the following choice. We have to specify a distribution, a conditional distribution like this, right? So this is the distribution that we choose. We're going to say that with probability q, y1 is equal to y1 hat, and with probability for whatever y1 hat we get, for whatever y1 we get. So remember, y1 was the output of the channel at the relay. And with probability 1 minus q, we're going to produce a symbol which is not in the alphabet of y1. So let's call this, and think of this as being an erasure symbol. Now, for this particular choice of a conditional distribution, let's go and evaluate the estimate and forward expressions. So we know that right has to be upper bounded by this quantity. This comes from the Cover-Gamal result. Now we're going to expand this using the chain rule. So we're going to get x and y, mutual information between x and y given x1. That's this term. And then we're going to get mutual information between x and y hat given x1 and y. And that mutual information we're going to write as a difference of entropies. So that's going to be entropy of x given x1 and y minus entropy of x given x1, y, and y1 hat. Okay, that's this line. Now we're going to use this form for the conditional distribution, and we're going to apply just the definition of conditional entropy. And so we know that with probability 1 minus q, there's y1 takes on a constant value, and so we can drop it from conditioning. And with probability q, it takes on the same value of y, of y1. Okay. That's what we get here. Okay. Now let's see. Now how do we combine this? And now it's easy because this minus this, it's q. No, it's not a cancellation. It's like, no, if you subtract 1 h of x x1 y minus 1 minus q h of x x1 y, you're left with a q h of x x1 y. And now, so you take q out, and what you're left with is the mutual information between x and y1 given x1 and y. Okay, so this is going to be our right expression, and you see now this is expressed only in terms of the 4 variables that are given by the channel. Okay, so that's something nice to start with, and this parameter q, which we're going to solve for in a minute. And we still have the feasibility constraint. So we have that mutual information between x1 and y has to be greater than mutual information between y1 and y hat 1 given x1 and y. That also comes from the Copywriting result. And if we do a simplification like this one, we see that this quantity becomes q of h of y1 given x1 and y. So now we know that we want to make q as large as possible, right? Because that's how we are going to maximize our right. But q has to be a number between 0 and 1, and it has to satisfy this constraint. So if we take this guy dividing down here and we set q equal to this, if it's less than or equal to 1 and equal to 1 if this is larger, then that's how we get our first achievability result. Note a couple of things here. We got rid of the feasibility constraint. These rates are achievable for any joint distribution. The only difference with decode and forward being that now we have to require that x and x1 be independent, because that's how we code. We generate code books independently at the transmitter and at the relay. So these two things have to be independent. But for any distribution of this form, these rates are achievable.
Yeah, but shouldn't your theorem somewhere say that you are assuming this quantization scheme? It doesn't. There is an implicit assumption that there's a particular kind of quantization they're doing at the relay, right? Which is this two-state quantization.
Sure, but that's in the proof, right? So I state my theorem. I say, these rates are achievable. So how do I show achievability? I have to show you a coding strategy, and when I develop that coding strategy, that's part of it.
Yeah.
All right. So the feasibility constraint is gone now. So that's the first piece of great news. These rates are achievable for any pair of independent input distributions, px and px1. There's something else good about this. And look at the following situation. If you have that this mutual information is positive, and this mutual information is the information that is unique about x that is available at the relay, that is not available at the decoder, right? So if there's some information that the relay can get about the source about the source message that the decoder cannot get, that's what this says. That's what this condition being positive says, right? And if you can send some positive amount of information from the relay to the destination, that's what this condition is saying here, then no, this term is positive, this term is positive, this whole term is strictly positive. Okay. Therefore, since this is the point-to-point rate, you can always send some, it could be infinitesimally small, but there's a positive amount of information that this strategy is allowing to go from the source to the destination using the relay. That already tells you that probably we have something, probably we're in the game, probably there's going to be some regime in which we're going to be able to beat decode and forward. Decode and forward, like we mentioned, if the relay is too noisy, the best you can do is just ignore the relay and send data on the direct path. This thing is going to allow you to use the relay even when the relay is very noisy. So that's something. However, the compression that is achieved by this guy is a rather crude form of compression. What we're doing is we are basically truncating the channel output. So think of this thing as you get a block of length n, right? And with probability q you send to the receiver the symbol that you got, and with probability 1 minus q you don't send anything. So it's like taking a block of length n, chopping it to a length of about nq, and then just sending this to the receiver. There's probably something smarter that you can do than this. Okay. But even if there's no claim whatsoever that this is optimal in any sense, this already gives you an idea that this way of getting rid of the feasibility constraint is not ridiculous, in the sense that it's allowing you to send some positive amount of information using the relay, and then we have to see how much more can we send than this. So now what we're going to do is we're going to consider a new chain where we're going to represent in the distribution in the original EAF. We're going to represent it as a concatenation of we're going to compress by doing two things. First, we're going to do compression as in the general EAF. Okay. Then we're going to do this form of time sharing, this form of truncation on the compressed signal. And that's how we're going to ensure that that the feasibility constraint is satisfied. So if we do only compression using this general form described in the original EAF, we're still left with the feasibility constraint. So we're going to do compression, as in the general case, but we're going to shorten that compressed stream using the truncation operation. And if we do that, then what we get is that here we divide by something. Remember, here we had an entropy, and here we have this mutual information. So hopefully we're dividing by something smaller. Therefore, we're making this number larger, right? And so in that way, hopefully we're achieving, we are sending some more rate.
So
this,
the original expression in the star, was it an entropy H? Okay.
Yes.
All right. So now you're describing some more general family of strategies
Yes.
that aren't just doing this.
That aren't just doing the truncation. Yes. That we're still doing the erasures because see here we don't have any feasibility constraints. Yeah. That was the whole point. Yeah. Pick an auxiliary variable that is not subject to the feasibility constraints. But but you still, but you have to pay something for that increase in rate.
So now what you're doing is you're not just simply letting y1 be y1 hat be y1. Is that what you're doing?
What I'm doing is I'm choosing a y1 hat as as an arbitrary map as before, and then I'm choosing a y double hat, which is going to be my y1 hat a fraction of the time, and it's going to be an erasure another part of the time.
So in some sense, this result says you can at best do what covariant algorithms say you can do.
Certainly.
And that time is 1. That starts.
Certainly.
Right?
Yes.
So you always do.
Okay,
So
you're
this is a
doing-
special case of estimate and
You're
forward.
doing exactly what it says on your slide. You're doing the compression of EAF, but then you're meeting feasibility by doing erasures.
Exactly.
Okay.
Exactly. That's the idea. I have to say, this is not so. Okay, so this is the statement of our achievability result. Oops. There. This is the statement of our achievability result, and we're going to look at, this is the end of the, somewhat more technical part, and now we're going to look at applications of this thing in concrete examples to gain some more intuition for what this means. Okay. But I have to say, when we started working on this problem, we didn't think that we were looking at a special case of estimate and forward. We were working on a different problem with Ron. It's this problem of having a broadcast channel with cooperating receivers, and this paper actually appeared this month in the December issue of the Transactions. So here we have an encoder, we have a broadcast channel, and we have two decoders which have links of finite capacity between them, and they're trying to cooperate to recover the original message sent by the encoder. They both want to agree on what was this message, and from the design of the conference between these two encoders, we knew, there we had found that truncation was a good idea in the sense that we were able to come up with a coding strategy that used truncations that increased the rate at which this encoder can transmit, and both of the decoders can agree. So, but this problem has an element of the relay in it. So that's how we first started thinking about how, if we, without all the noise of all the non-essential parts due to the broadcast channel, if we focus just on the relay component, what can we say based on truncation? So that was one motivation to look at this. Another one is that I didn't get to talk much about this here, but let me very quickly say that we were also, in parallel with this, looking at a modification to this receiver. Instead of doing this sequential process of first using Y to recover the bin, then using the bin and the previous channel output to recover the approximation transmitted by the receiver, and then using the approximation of the receiver and the current channel output to recover the source message. Instead of doing this sequentially, since we were interested in the case where we have a noisy relay, because we know that in the case where the relay is not too noisy, the decoding forward performs quite well, we thought of combining these two steps into a strategy that we called a joint decoding strategy. So, since there's a dependence between the reconstruction Y and the what is it? Hold on a second. The approximation Y and the transmitted message, right? The message sent by the encoder. Since there's a statistical dependence there, we thought that maybe by explicitly exploiting that statistical dependence, we would be able to get an increase in rates over the estimate and forward. Right? So that's that's how we started looking at this thing. So we wrote our paper, we sent it to the transactions saying, hey, we have a way to improve over estimate and forward. And Gerhard was the editor and Shlomo was the reviewer. And they told us, no. What you have is a special case of estimate and forward. And so that's why we acknowledged their contribution, because really what happened is that I think we started understanding really what estimate and forward was after they showed us that all the work that we had been doing was actually a special case of the general strategy. So now back to your question, yes, there's no way we can do better, because what we're doing is it's a special case. We're choosing the auxiliary variable and we're choosing the conference in a way such that it leads to simpler expressions.
You're imbibing the constraint and there's a gradient.
Yes. Yeah. Okay. So that's that with respect to that description. So now we're going to apply this coding strategy in two different scenarios. And the first one that we're going to look at is the case of multiple relays. What time did we start?
We have time. When did we start? 2:30.
Not really. We started
2:45.
maybe 2:40 we started.
Yeah, so you have at least
Okay.
another 20, 30 minutes.
20 minutes should be good. Yeah, 10 for each. Yeah, good. Okay, so in this part, we're first going to look at the formulation of the relay channel with multiple nodes. We're going to describe a generalization of the TS-EAF result to the case of multiple relays. And then I'll show you one example where with multiple relays, our coding strategy delivers higher rates than DAF as well. Okay, so the discrete memoryless relay channel now with multiple relays. Same setup as in the previous construction. The only difference is that we chose to do the figure now for two relays. You have two channel outputs seen by the two relays. You have two channel inputs injected by the two relays, and then you still have the input of the encoder and the output seen by the decoder. Okay. So a few more parameters, but the exact same setup as before. What is known about this problem? Well, there is a paper of Xie and Kumar that appeared sometime last year where they give a generalization of decode and forward for multiple relays. Obviously, since their strategy is based on decode and forward, the limitations of the basic decode and forward still applied to this problem. There was also a paper of Gerhard and others where they applied estimate and forward with partial decoding of the relays to the multiple relay scenario. And that's the case where I say that even for two relays there were 9 feasibility constraints that needed to be satisfied. So basically the difficulties with estimate and forward that we talked about before, that it's too general, that we cannot even compare it to decode and forward, things of the sort, become even more severe with multiple relays because of the quick increase in the number of constraints with the relays. So what we're going to do is we're going to use this time sharing mechanism to obtain a computable achievability result for multiple relays. So that's the goal for this part. And how is this going to work? The transmitter is going to transmit just as in the single relay case, and the receiver, what is he going to do? First, he's going to decide on a decoding order for the relays. So all of these relays are going to send one message to the one bin index to the receiver. But all of these bin indices are going to refer to the same information. They are all noisy versions of the signal sent by the transmitter. Right? So there's gain to be had in choosing a particular decoding order. So decoding one message from one relay may help you not only decode the message from the sender, but it may also help you decode messages from other relays. Right? And since now you have extra information, then maybe you can increase the rate from those other relays. And by increasing those rates, you get more information about the source message. So you see how.
I didn't see in your channel model. Are you saying that the second relay who transmits is able to use some? Okay, all right.
All of them do the same thing as before.
Right.
The transmitter picks a waveform, puts it into the channel. All the relays are going to observe a noisy version, are going to do a truncation, a compression, and are going to send an index to the receiver. So basically, what happens is that we're going to simplify this expression in a minute. We're going to look at a case with two relays, and we're going to see exactly what all of these quantities means.
So are these relays cooperating with each other, or they're all just doing?
They're not. The only way in which they cooperate is by agreeing on the rate on these queues So there's going to be one queue per relay, and that queue is going to be chosen not independently.
Okay.
So the rate,
So there is some correlation across the QIs.
the QIs are parameters that they're not random, but they are chosen so as to maximize this total rate.
But isn't the relay 2 going to send an index in a way that reflects the fact that he uses the fact that he heard the transmission of relay 1?
He didn't hear the transmission. Oh,
Yes, he
that's
does,
what I was
right?
looking at your channel model. It's like
Hold on.
when relay 1 sends, right, it alters what relay 2 hears, right? Because you have a.
that is correct. That is correct.
So
All that information is going to be used only at the decoder. All the relay does is it listens to some it gets some waveform. Whatever that waveform is, it will.
waveform from the encoder, from the sender. The original
From the channel. There's going to be a channel.
Okay.
There's going to be a Y1 observed at relay 1, which, like you correctly pointed out, it will be influenced by this xn, by this x1, and by this x2. So this Y1 will depend on this x2. But all the relay will do is it's going to listen to this Y1, it's going to compress it, it's going to truncate it, and based on that, it's going to choose an index that it's going to determine this x1, and then all those correlations that you're pointing to are going to be exploited at the decoder.
So why does the sequencing matter?
Because what will the decoder do now? The decoder will first decode one symbol. It will decode the message from one of the relays. Then he will, according to the order that was picked. Sorry, waxed. I didn't see. There. So the decoder is going to pick an order and it's going to say, first I'm going to decode the message from relay 1. Suppose that the decoding is successful. Then he knows what was the x1 that was put into the channel. Right? And so now x1 becomes known. So now he can use knowledge of x1 in decoding the message of x2. He's able to cancel the effect of this when he goes to decode x2. So it's like the channel becomes less noisy by doing that.
But is it that does the decoder have to do that, or can you just wait and get all of the x1, x2 And when it gets them all, do some joint decoding. I mean, you're sort of saying you're just doing a particular form of joint decoding, so the successive version.
Right. Right. That's the form.
You're like sort of to make the analysis simple, or is it? Or do you know if you're sacrificing something doing that? Well, you're not.
Do I know?
But maybe there's no.
Do I know if we sacrifice something by doing that?
Or if it doesn't,
I don't know.
it just has achievability.
No,
Yeah, so it's an achievability result. No, but his question is valid. So it's not an issue of whether it's right or not.
The converse.
Right. Forget about a converse here. I mean, we're happy to get. Look at how difficult this problem is. We're happy to show that we can send an infinitesimal positive amount of information using the relay. Forget about achieving capacity or anything of the kind. But we're so far away from that. That's why the title was like a tiny bit of progress.
So the X vector there is all the signals from the relay in the rate expression, the first expression?
The X, this X corresponds to, yes, the input of the channel and the input of generated by the transmitter and by all the relays.
No, how can it be?
No, sorry, not the transmitter. Only the relays. Only the relays. Yes, sorry. Because this is what, in the case of only one relay, this was X1. So with more relays, it's X1, X2. Yes, I'm sorry. Yeah. Okay. And then there's this ugly quantity here that we're going to see in a moment what it means. Okay. So and we do that with this concrete example.
I have a question. I'm going to interrupt again. Even at the single relay case, when you do just truncation, what did you send on X1? I forgot. You had Y hat was just truncated Y1, right? Y1 hat was truncated Y1. So what was X1? You go back one more slide, right? Okay, one more slide.
There.
So what did you send as X1? Because
I'm
it's
trying to
not like some
understand
complicated Y and Z. You're just basically truncating your receive signal. So how did you do a message passing to the destination?
Well, I'm taking the truncated signal, and that's going to be my message. Right. So now I'm going to, for all these truncated signals of a certain length, I'm going to get one different index for each, and this index is going to determine a block of X's. That's what I'm going to put into the channel. Good. Yeah, good point.
Yeah, so 2 to the n r prime, whatever that rate was. And
We'll see where that 2 to the n comes from now. Let's look at this example. 2 relays, and remember we're trying to show that this particular achievability strategy gives us an improvement over decode and forward. So just showing a positive improvement would make it the best EIF strategy, and that's what we're getting here. The destination is going to decode these messages independently. So that's a further simplification. Okay. So instead of choosing choosing a particular order and doing this successive cancellation that we were saying before, the destination, all he's going to do is that in any arbitrary order, without trying to do any successive cancellation, is going to decode the messages from all the encoders, from all the relays. And so it follows from the previous proof, these are the fractions of time that each one of them should be operating. Now, what is the rate that we're going to achieve? Well, this is the point-to-point rate. Right? It's mutual information between input and output to the channel, given the signals decoded by the two by the two transmitters. Now, a fraction q1 of the time, we're going to have a signal coming from relay 1, and a fraction 1 minus q2 of the time, we are not going to have a signal coming from relay 2. Okay. So the extra information that we get is this one when transmitter. This is the extra information that we get on the path from the source to relay 1 to destination when only relay 1 is transmitting. And that happens a fraction q1, 1 minus q2 of the time. We get the symmetric condition, a fraction 1 minus q1, q2 of the time. We're going to get information flowing from the source to the second relay to the destination. And that's this quantity and this quantity here. Okay. And a fraction q1, q2 of the time, both of them will be sending. And this is how much information is going to go from the source to both relays to the destination. You see now where this is coming from. Right. We have to look at all possible configurations of relays transmitting or not transmitting, right? And we have 2 to the n minus 1 such options. And when nobody's transmitting, then you get only the relay term. This mutual information is a compact way of representing all of these subsets, and this symbol here is a compact way of representing all of these combinations of Q1s and QIs and 1 minus QIs. So for this particular setup, for this particular configuration, I just ran some numerical simulations. We said, okay, we know that we have to make the mutual information between the source and the relays to be very small. Right? If we want to find, so we're looking for a channel such that the mutual information between the source and the two relays is small, and where we can evaluate this expression here, and we run a lot of random guesses.
They are doing joint decoding. It's that those are the times when one or the other is not transmitting.
Here it does seem that way.
Yeah?
In the other one it seems different. So this numerical example, like, is it binary channel? I mean, there are discrete channels, right?
It's this is all, but this is all binary. Yes, the paper is the example is fully described in the paper.
But somehow, like so there's two relays, but when you say decode and forward,
yes,
you're requiring both relays to decode?
No, in this particular case, the maximum rate achievable with decode and forward is less than the max, because we have these two noisy relays, is less than the maximum rate achievable with by just turning them off completely.
So decode and but it's a decode and forward for both relays.
Yes, for both relays. Yeah. And our TSEAF gets just enough to.
The problem is it's 0.01 or 0.006 something.
It is.
Compared to 0, it's infinitely large.
That was the point. Yeah.
So like basically you're choosing, like, this formula says, you're choosing random erasures with respect to each relay flips a coin and decides to erase.
Right.
Like, can't you think about the erasures as a sort of a random vector and choose correlated erasures of the nodes? That there might be some policy of a structure erasure to the erasures? That like wouldn't it would be the same expressions, like the same terms, but with different probabilistic weights assigned to them? That
Honestly,
but is that possible or not? Or is that idiotic?
honestly, I have no idea.
Okay.
I have a hard time
The channels
picturing how that would go.
With the same
Because-
marginals, right?
Yeah, but hold on a second. Originally what we were trying to do was, in the first paper that we sent to a transaction that came back with the comments, oh, this is all a special case of estimate and forward. We were describing the operation in terms of blocks, and saying we're going to truncate these blocks. We're going to send only the initial segment, the segment that we can transmit. It turns out that operation, just choosing an initial segment, the rates that you can achieve are equivalent to the rates that you can achieve with this random mechanism. Now, if I were to describe, you see,
Is that just
this
because
rate,
joint typicality doesn't care if you get sort of
what
casually the reason?
what I'm trying to
doesn't matter.
what I'm trying to get at is the following: we need a single letter description here.
Yeah.
Okay, so how would I give a description of some process with memory? Because that's basically what you're saying. By introducing dependencies between the erasures at different parts of the block. I'm not sure how.
No, I wasn't thinking there'd be dependencies at different times. It'd just be some distribute. If you think of Q1 as a variable, relay 1 erases or not. That vector of Q's, like at each time you have some vector of choices. And you
Right, so it's not a coin flip.
vectors IID without any memory, but you choose them with a non-binomial or binary kind of distribution.
And what does that vector do? What does it specify? So if I have one parameter at one time, I know what it means. It's either I erase or I don't erase at this time. So what would the vector tell me?
Well, sometimes maybe if user 1 decides to erase, then user 2 doesn't. Like for instance, you can have a thing where
You're talking about
where maybe
correlations between the
erasure.
Across relays. I thought you were talking about for over time for a block.
No,
That's what.
trying to make something that generalizes this formula, right? That gives you more flexibility.
So that if someone is,
So instead
it's
of
an interesting observation.
I don't know.
I don't know what I would do with it, but I would be surprised if it didn't lead anywhere,
It
because
has to be a little better than this because this is just one choice, right?
Right.
What is the number you would get if you just had one of the relays on in this particular example?
in this particular example,
Yeah.
the way in which we get this rate is by turning off one of our
Okay,
relays.
so essentially that's what
That's what came out of the simulation. So decoding forward is free to use both relays, and the best that it can do is this. And with only one of the relays, we can get this. That's what came out of that simulation.
Yeah, but there are all these combination strategies. So it's some kind of strangely noisy channel to both relays.
Or is it just that relay 2 is a really noisy
Even
channel?
noisier.
Is that it's better to just ignore whatever? Is that the
Would,
fact that you end up with relay 2, he's erasing everything?
A
Or is it
relay.
the other way around?
Yeah.
Yes, you're basically shutting off relay 2 in this example. So using only one relay is enough for you to get a gain over the point-to-point rate. Yeah. now that I understood it better, you left me thinking. Now I think I actually liked the suggestion of, what would happen if one of the relay, if you introduce dependencies in when the relays erase. So if one relay erases, that makes another relay less likely to erase at this time.
Exactly.
Right now, the relay.
Well, but hold on a second. Wouldn't you need communication between the relays for that?
No, I think you just have them each know some joint distribution.
Yeah, but they're all independent in these kinds.
Oh, you have to communicate again.
Right. They would, or you need access to a common source of randomness.
It's an optimization then.
All right, so then I'm cheating, I guess.
You have to supply more information.
Yeah.
You have to let
Okay.
all of them have access to a common source of randomness, for example.
Yeah.
Something of that kind. Yeah. No, but it was a good, well, didn't go very far, but I liked it while it lasted. Okay, all right. The second example, I thought that the previous part was going to take 10 minutes. So let's try to go a bit faster on this. The Gaussian channel, you had some question about this before. So we're going to consider a special setup of the Gaussian channel. And that's a setup where the relay sends, the link between the relay and the decoder is orthogonal to the link between the encoder and the decoder and the decoder and the relay, and the encoder and the relay.
So it's like the Lian Viravelli model. Grace's model is also. Yeah.
She had a broadcast channel as well there, didn't she?
Yeah, but she also worked on this for research
Oh.
allocation.
Okay. No, I think I've seen that. I think she sent me the paper, but I don't think I read it. But yeah, I think I know which work you're talking about. We don't claim that this is any original contribution of ours. I mean, many people have looked at this setup before. Okay, so the thing to notice here is that since here there's no the output of the relay does not influence either either the channel input of the relay doesn't influence the output seen by the relay or the output at the destination, we can basically forget about X1. Okay, and so what we're going to focus on here is on the design of this map. So, taking into account the fact that we can forget X1, we see that if we specialize the general EAF expressions, we get this quantity here where we drop the conditioning on X1. And here what we had was mutual information between X1 and Y. Now this is replaced by the capacity of that orthogonal channel. And this has to be greater than this quantity where we also drop X1 from the conditioning there. That's how we specialize the general EAF to this particular setup.
So the Y hat received at the destination is on an independent channel, right?
Yes. Yes. What are relaying strategies commonly used for this channel? Well, there's the standard decode and forward with Gaussian codebooks. So you generate a code, you decode at the relay, and then you send an index as a function of that decoded message to the destination. There's estimate and forward, but now with a pure Gaussian mapping. So that means that basically you get your Y1 hat by taking the output Y1 and adding some more noise to it. That's how you're going to do the compression. Okay, and this quantization noise you want to make as small as possible to maximize the rate of information that you can send at which you can send this Y1. And then there's also the amplify and forward strategy, which in this case consists of taking the channel output, shifting it to a different frequency band, scaling it properly, and sending that to the receiver. Now, we're going to look at the case where the transmitter uses some form of coded modulation, for example BPSK. And why do we do that? The first reason, because we were not able to think of a better strategy than this. So our choices of auxiliary variables, in this particular case, when the input when the input to the channel is also Gaussian, it becomes trivial. I mean, the solution to our problem consists of setting q equal to 1 always, just never truncate. And so our solution doesn't we don't get any interesting result for this case. However, if we use BPSK, then the output Y1 is not Gaussian anymore. Okay. So it's going to be a Gaussian mixture of this kind. And there's also the nice thing that we can always say that this gives us some insights into the design of practical systems. So we're going to look at the mapping, at this mapping that we should do when we use BPSK, and in this form of BPSK, and in this case it's natural to consider a ternary map. And what is that ternary map? Well, we're going to do a symbol by symbol decision of what was the bit received, but we're going to allow for an erasure of the unreliable decisions. Now, it turns out that this is not going to be the optimal map to use. Oh, not the optimal. It turns out that this is not going to be the best map that we could think of, but there's an element of this map that is useful. So another map that I want to show you, which is a bit closer to the time sharing mechanism that I was describing before, is the following. So what is going to be the distribution of Y1 hat? If our Y1 is positive, then we'll send a symbol 1 with some probability, and we'll send an erasure with the complement of the probability. So this is how we're going to do our gating. If Y1 is negative, then what we send when we don't erase is a -1 instead of 1. Okay. So it's still Y1 hat is still a ternary variable. It's still a ternary map, but like this one. But the mechanics are different. Now, it turns out that neither one of these is going to be optimal, because as we will see in a plot in a moment, when there are going to be cases where, like for example, if the capacity of the link from the relay to the destination is very small, then the fraction, then to make Y1 hat have an entropy that fits in the capacity of that channel, we would have to erase a very large fraction of the symbols, and so only very rarely we would see an observation that is really strong, really reliable, and when we see it we can send it, but those don't happen very often. Okay, so the signal that we generate in this using this map is not going to help much in cases when the link from the relay to the destination is noisy. On the other hand, when we have a high SNR situation, a symbol by symbol decision is going to be almost as good as the code and forward. It's good, as SNR goes to infinity, this strategy does approximate the code and forward. Right? So some combination of the two, where the low quality decisions we erase deterministically, and the higher quality decisions we gate according to our truncation mechanism, then that's going to be the structure of the map that we're going to analyze. Yes?
In other words, you're saying that actually in the signal noise goes to infinity, repetition code suffices?
A what?
It's a repetition code, right?
It's not a repetition code.
Well, it's noisy, but it's the relay is just sending whatever it received. You just said, didn't you just say if the signal noise goes to infinity, this achieves the same as decoding code? Isn't that what you just said?
Yes. But then, but hold on a second. So I'm going to get, so what is this going to do? I'm going to get my, I'm going to get my vector of y1s at the relay. And I'm going to apply this symbol by symbol decision. Okay? And I'm going to reconstruct, in the limit as SNR goes to infinity, I'm going to reconstruct the message sent by the transmitter. So now, as a function of this whole message, I'm going to choose my input to the channel. That's what decode and forward does. And that's what this thing is doing as well. Because at high SNR, then, you know, at high SNR, having this positive or, you know, or this negative is going to give you exactly the symbol that was put into the channel by the transmitter. So the relay gets to see that that as well. Okay, and so we have a lot of plots in the paper, but the one plot, the one point I wanted to show you was this trade-off between the two strategies that I was describing before. So what do I want to focus your attention on? Look only first at these three red lines. Ignore everything else. Just focus your attention on these three red lines. This is the deterministic hard decision when we have a low capacity between a low capacity link between the relay and the destination. And this is the this gating mechanism, the second map, and the solid line is the optimal combination of the two. So we see that it's like what I was saying before. With the deterministic mechanism, in this case, we have to erase too much information, and the information that we can send to the from the relay to the destination, it's not particularly helpful. I mean, we help a lot more by sending a few decisions which are less reliable, but you know, but choosing them randomly. Now,
so do I understand this graph right? G is the gain from the relay to the destination.
Yes.
And
No. G is the gain from the source to the relay.
See, it's a link. It's a fixed capacity link from relay to destination.
And that's what we're fixing with this
okay,
C.
it's the other way around. So
Yes.
Okay, I was gonna.
G is this G. Okay, and C is this C. Okay, and what I should have started by saying what I'm plotting, right? Okay. Yeah. So G is that G. This C, these red lines correspond to a fixed C of 0.4, and the rate on the is the rate. The rate of transmission. That's what we're plotting on the vertical axis. And so when the rate from the relay to the destination is low, so when we have a narrow pipe from the relay to the destination, then the signal that the deterministic hard decision can send is less useful than the signal that can be sent with the other random mechanism. And if you combine both of them optimally in the strategy that I gave before, you get something that is a slight improvement over this one. If now you consider, now I want you to pay attention to the green lines. And in the case of the green lines, what we get is that, well, the solid green line is again the optimal combination of the two. This one is okay. So this one here is the deterministic hard decision. So initially, for low SNRs, it performs worse than the optimal, but then very quickly it jumps up, and then they from this point on they go together. So I doubt that you can see it, but the dashed line is almost on top of the solid line here. And at the same time, the solid line for not the solid line, the other one, the coin flipping strategy starts on top of the determinant of the optimal one, and then it diverges and is dominated by the other strategy. So here goes the other green line. So what's the point that I'm trying to make with this? The actual numbers don't really matter. The point here is that why did we look at this particular example? We wanted to see what we could learn about the interplay between the different parameters in the problem. So there seems to be some relationship between the cardinality of these variables. So at high SNR, it looks like a variable of cardinality 2 seems to be optimum. At lower SNR, that a variable of cardinality 3 seems to be optimum. At even lower SNR, as we'll see in the next figure, Gaussian quantization is optimum. That means a variable with a very large cardinality. So we wanted to understand how all of these things interact with each other. And it seems that the gain in the channel, the capacity of the relay link, the cardinality of these auxiliary variables, these things all seem to depend on each other in ways that we're only beginning to form conjectures now about what they are based on this. One other plot that we made is that this thing is still running. I mean, these blocks are there only because computing each point in each one of these points. So there's a point for each intersection of a line here and a line here, and computing each one of those takes hours of CPU. So we looked at, for each combination of relay link capacity and channel gain from the source to the relay, which of these strategies would perform better. And we know, by the way, this is all based on simulations. So when I'm talking about, when I say here that decode and forward achieves capacity, what I mean is not that I have a theorem that says that decode and forward achieves capacity for some range of parameters. What it means is that the difference between a numerically computed upper bound and the rate of decode and forward was less than the precision of the numbers that we were working with. So it's in that, careful there, it's only in that sense that I say here that DAF achieves capacity. There's another regime where DAF does not achieve capacity, but it's still better than this time sharing mechanism that we proposed. There's another regime where our time sharing mechanism dominates, and there's yet another one where Gaussian quantization is optimum. And this seems to depend on a combination of SNR and link capacity. So the plots seem to be forming to indicate that there's something, that there's a region that looks something like that. So that simulation still, has been running for, let's see, we sent the paper in October. It's been running since mid-November and it's not done yet. So it really takes a while to compute these things. Or we have a lousy machine, one of the two.
So you just sort of every hour or two it produces a new graph?
It produces a new point. And every day or two.
Wow.
Yeah, it's a slow one.
Each point is basically, each point you're evaluating all four strategies.
Yes.
And coloring with the,
and picking the best.
Okay.
Yeah. So to wrap up this part, and I have only 2 slides left, so I promise the torture will end soon. Let me recap. this thing. So I already said most of what's in here. The only point that I want to emphasize is that about this issue with the cardinality bounds, it really seems like this mapping that we proposed will achieve capacity at high SNRs because it essentially behaves like the code and forward. It dominates both the Gaussian mapping and the code and forward in an intermediate range. So if somehow, and this is something that we don't know yet how to do, but it seems that if somehow we could construct a map not with three variables, not with three symbols, but a map that somehow picks the number of symbols depending on the configuration. So it's like saying, suppose we have an infinite alphabet, but the distribution that we put on this alphabet assigns non-zero probabilities as a function of the channel conditions. If we could establish that, some connection like that, that would suggest that that there has to be a continuum here. This is an optimum for an auxiliary alphabet of size 2. This is an optimum for an auxiliary alphabet of size 3. If we could create a continuum of plots here, maybe we'll be on our way to getting closer to the to solving the capacity for this problem. So that goes, I wanted to talk a bit about that because that goes to your question of before. Is the Gaussian setup easier? Well, yeah, there are some things that we're trying, but it's by no means straightforward. At least we haven't found a way to make it straightforward. Okay, so that's that. We considered the relay channel with an instance of the EAF strategy that is the feasibility constraint is always satisfied. We derived the set of achievable rates for a multiple relay scenario, and and we saw that it's not a trivial set of achievable rates, that it actually gets something that other strategies didn't get before, and we looked at the at the Gaussian channel with coded modulation. So this is my last slide, okay? And I want to say why I'm looking at these problems. Okay? And the reason is because these problems, multiple access channels, broadcast channels, relay channels, distributed compression, distributed modulation, distributed time synchronization, all of these questions come up all the time in